Okay, so today we're going to start looking at hybridization in carbon, which will probably absorb most of today's lecture, if not all of it, and so we move on from there. I do want to apologize. I'm expecting a really important phone call, so I have my phone on, and if they actually call, then I'll stop the lecture and then take the call and then start it back. Okay, so let me apologize up front if I have to disturb the lecture. Okay, so one of the last things we did was looked at the interaction between atomic orbitals. And the case we examined was really the simplest case, which is the molecular orbital picture of 1s orbitals coming together. Right? So we looked at the hydrogen atoms. That's my nucleus of the hydrogen. And then the other hydrogen atom, and that circle represents a sphere, which is the 1s orbital. And again, there is no skin on the orbital, so this is in many ways a terrible picture. So those orbitals came together, they interacted, and you ended up with two molecular orbitals. One looked like this, which we call the sigma star, 1s, and then the other one looked like this, which we call the sigma 1s. And the sigma 1s is more stable than either the atomic orbitals, because we have energy on this axis. The sigma 1s is more stable than either the 1s atomic orbitals or clearly the anti-bonding sigma 1s star, sigma star. And we said that essentially the difference in energy here, this is the same as the energy gap here. But what's important is that atomic orbitals, two atomic orbitals, merge to form two orbitals, two molecular orbitals in this case. So there's orbital conservation. If I put in two orbitals, I get two out. If I put in n orbitals, or x orbitals, I'll get x orbitals out. Also, these atomic orbitals are called atomic because the electron density bounds a single nucleus here, right? So this electron density has nothing to do with that nucleus. It's localized, if you will, and that's a bad word for electrons, but bear with me, it's localized over a single nucleus. So a single atom. So these are atomic orbitals. In this case, the electron density, right, represented by the oval or these weird-looking loops, the electron density encompasses two nuclei. So this is now a molecular orbital. So atomic orbitals can interact so that they form molecular orbitals. That's the example we have here. And we also see that there is orbital conservation. The number of orbitals I put in is the number of orbitals I get out. Okay. Well, we're going to use this as sort of a template, and I'm just going to get an eraser. We're going to use this as a template for understanding some things in the bonding of carbon. And I will just point out here that if you look at the energy level diagrams, clearly hydrogen has access only to the 1s orbital, and so all of its chemistry happens from the 1s orbital. But carbon is different, right? Carbon is element number 6, so I also have access now to the 2s and to the 2p orbitals. So carbon has 6 electrons according to the off-bore principle. The first will go into the 1s. The second, according to the Pauli principle, will spin pair. So that's 1s2. And then the remaining 4 electrons will go the first of the 4 into 2s. That's off-bore principle again. And the second will spin pair. Right? So that's 2s2. The remaining 2 electrons fill according to Hund's rule. which is that they will fill singly with the same spin into the 2p orbital. So I'll occupy 2p with a certain spin, up or down, doesn't matter. So let's call this 2px, then 2py, then 2pz. And we call them x, y, and z because of their orientations in space. So x is on the x-axis, y along the y-axis, z along the z-axis, in that frame. So I can then write that the electronic configuration of carbon is 1s2, right? 1s2, 2s2, 2s with 2 electrons, and I can write either 2p2 or, in more detail, 1s2, 2s2, 2px1, 2py1, and for the moment I'll write 2pz0. Right? So 2px1, 2py1, 2pz0. It's not customary to indicate the vacant orbitals unless there's an intention, as your discussion proceeds, to somehow occupy those vacant orbitals, right? Unless it's somehow germane to the conversation. Okay, so let's keep that in mind. So what we're going to do is look at some of the hydrocarbons that carbon forms, and we're going to see how the formation of those hydrocarbons is linked to the electronic configuration of carbon. So I will point out that in general, when we form a bond, right? If I have, let's say I have an atom with a nucleus and an electron, and another atom with a nucleus and an electron, and this is stuff you'd have learned in high school chemistry or Gen Chem. Typically, when we form a bond, in the typical sense, each atom brings in one electron. So there's an electron pair being shared. And I could represent that by saying A brings in one electron, let's say B brings in another, and together we form the A-B bond, right? And that dash indicates the electron pair that's being shared. And that's what's called a normal covalent bond, right? But I could potentially have A being the donor atom, bringing in both electrons, and B being the acceptor atom that doesn't bring anything to the party but a vacant space, a vacant orbital. And that will generate exactly the same AB. And in fact, the AB is indistinguishable. The AB formed by this type of covalent bond formation is indistinguishable from the AB formed by each atom bringing one. So whether I have a normal covalent bond, or what's called a dative, this is called a dative, or sometimes called a coordinate bond. So whether I have a bond formation that is dative or coordinate, or by the normal fashion, each bringing one, the bonds are indistinguishable. They're identical in length, in strength, in polarity, all of those things. So that's just a reminder to keep in mind as we go on through the rest of this discussion. So on to carbon. So we are going to examine initially the simplest hydrocarbon, which is methane, which has the molecular formula CH4. If I were to examine methane, what I would find is that the methane molecule has certain features. One, the carbon is tetravalent. Right? So clearly the carbon is forming 4 bonds to H. 2, all the CH bonds are identical. They have exactly the same length, they've got the same strength, they've got the same polarity. In every measurable way, all the bonds are identical. It is also tetrahedral. right? In other words, the carbon sits at the center of a regular tetrahedron. So H, 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 H. And you remember from your Gen Chem, the bond angle of a tetrahedron is 109.5 degrees. And that's true for all of these. Now, I will remind you, and you would have met this in Gen Chem, lines that are drawn like these are for bonds that are in the plane of the page, or in this case, in the plane of the board. Okay? So I've got H, C, H that are in the plane of the board. The wedge, which is sometimes written as a full wedge, like this, it doesn't really matter. The wedge represents a bond coming out of the board. So clearly it gets bigger, right? It gets bigger as it approaches you. So I have this H is actually here, physically in front of the board. So H, C, H are in the plane of the board. This H is physically in front. And the way I represent it being in front in two-dimensional space is to use a wedge. On the other hand, this H, the dotted line indicates that it's receding away from you. So it's behind the board. So I have an H in front of the board, and I've got an H behind the board. And the bond angle is 109.5. Now you'd have met this in Gen Chem, so this is sort of a reminder. Okay, what I want to do is to explain the bonding of carbon in methane using the electronic configuration of carbon. Now, we will ignore the 1s2 scenario. And why is that? Chemistry happens with valence electrons only. The valence electrons are the ones that define chemistry, which is why we spend our time with group numbers in organic chemistry, because they tell us the number of valence electrons. And obviously, the reason that is the case is that if I have an atom, and in this case I've got 2 electrons in the core, and I've got 4 electrons outside, well, when this atom bumps into another atom to do chemistry, the only electrons that interact are the ones at the surface. Right? The core electrons are hidden, they don't interact. Right? They're not involved in chemistry, so I'm going to ignore them. If you're walking down the street and you bump into a stranger, all you will exchange with a stranger is sweat, maybe some fabric from your clothing. You don't exchange kidneys, you don't exchange a heart. Right? I mean, those things are internal, those are core, they're not part of the contact. Okay? So we are only concerned with the valence electrons, not the core electrons. Okay. Well, here's the problem. Oh, in fact, I could have left it. Here's the problem. We said that when atoms bond, typically one of two things happens. Either A brings in one electron and B brings in the other. Right? So you get your AB bond. Or A brings in both and B brings in none. Or B brings in both and A brings in none. So what this tells me is that the number of bonds I form is related to the number of unpaired electrons that I have. If I have one unpaired electron, I can form one bond. 2 unpaired electrons, I can form 2 bonds. And so on and so on and so on. If I look at the electronic configuration of carbon, right, I've got a pair of electrons, and then I have 2 unpaired electrons. Carbon should be divalent. I've got 2 unpaired electrons, I can form 2 bonds. So when carbon bonds with H, what I would have expected is, so here's my carbon, here is the H, each H has 1 electron. Right? Each H has 1 electron. So what I would have expected, based upon the electronic configuration of carbon, is that carbon should form, when it bonds the hydrogens, CH2. Right? What would have happened is that the unpaired electron of the H overlaps with this unpaired electron of the carbon. Same thing happens here, and I should have made CH2. So carbon should have been divalent. Now, I can make the argument that what might happen is that maybe it bonds with H's to form two normal covalent bonds, and then uses the lone pair, right, to bond with an H that has no electrons and form another bond. Okay, and all the CH bonds will be the same. But if that's the case, the H would have had to come in with no electrons, and that is H plus. So given this configuration of carbon, it should have formed two versions. Either a neutral CH2, or the CH2 would then bind with H plus, H devoid of electrons, and that would form CH3 plus. In other words, from that configuration, carbon should never form CH4. Carbon should not show tetravalence. Right? So the two unpaired electrons, I grant you that I can form two bonds. I could take a stretch and say the remaining lone pair can form a dative bond with an H, but that H has to come in without electrons, so that's an H plus. So at best, carbon should show trivalence, but even then, the species will have a positive charge. CH4 is an anomaly. Whenever atoms bond in a fashion that is not consistent with their electronic configuration, we invoke a concept called hybridization. Okay, let's just see how that plays out. So we're aware that something funny is happening. All right, so can I fix that? Can I make an argument to help to move this forward? The answer is yeah. If I want tetravalence, which is what the carbon is doing, I need 4 unpaired electrons. So what I can do then is I can say, look, I've got 2 electrons in the 2s. Why don't I take one of them and put it in the vacant 2pz? Okay? Now what will that require? It requires the input of 2 quanta of energy. The first quantum of energy is required to unpair the electrons, right? So let's just make sure we understand the concept here. So electrons are negative. How is it that 2 negative particles, 2 electrons, could occupy an orbital together, right? The 1s orbital, the 2s orbitals are very small. If you put 2 negatively charged particles, or for that matter, 2 positively charged particles, in the same volume of space, they should repel. So how is it that I can have 2 electrons in the same orbital? There should be massive repulsion. The answer is yeah, there is massive repulsion. And if there is massive repulsion, it means as big as the repulsion is, there must be a greater force of attraction between them. So when you add the repulsion and you add the attraction wins out. And as long as there's attraction, there's a bond. What's the source of the attraction? Well, if you remember from your Gen Chem, you can imagine the electrons as having a spin. And if you have any charged particle that is undergoing rotation, that charged particle generates a magnetic field. So the electron spinning clockwise will generate one pole of a magnet. The electron spinning anti-clockwise generates the opposite pole of the magnet. So you end up with, superimposed upon the electronic repulsion, you end up with a magnetic attraction, north pole and south pole. And the magnetic attraction is stronger than the electronic repulsion. And that's what keeps the electrons together in the same orbital. So if there's a force of attraction, what we call the pairing energy, that's the bond, if there's a force of attraction, in order for me to move this electron here, the first thing I have to do is to unpair the electrons or break the magnetic attraction. That requires the input of energy. Okay. Even after I break the bond, I must now provide that newly unpaired electron this much energy to jump the gap between the 2s and the 2p's. So I'm putting in two different sets of energy. One is the pairing energy to unpair the two electrons to break the magnetic attraction. And the other is what you might call a promotional energy to bridge this gap, this energy gap between the 2s and the 2p. So what that tells me is that if I take this system, right, if I take that system, which I'm gonna write now as, I'll write it here. So I have 1s2, which I'm gonna pretty much ignore, 2s2, 2px1, 2py1, 2pz0. I'm gonna call this the ground state. The ground state, the basement level. That is the lowest energy scenario. And why is that? That is the one that's predicted by the off-Bohr Pauli exclusion principle Hund's rule. That's the way the electron should behave as they fill orbitals. That's the most stable scenario. So that's the ground state. Clearly, what has happened when I move the electron from here to here, so you can imagine taking one of the 2s electrons and then moving it into the 2pz. That species is more energetic relative to the ground state. So we're going to call this the excited state. And the excited state is going to be 1s2 because we are never touching the core electrons. But it's now 2s1 because I've moved one of these electrons here. Right? So it's 2s1, 2px1, 2py1, 2pz1. That's an excited state. It is not what the rules predict. It is not what generates the most stable configuration. It's clearly not because I've moved electrons from the more stable 2s into the less stable 2p. By the way, if I were to draw that configuration, what it would look like, right, would be somewhere here. I have my 2s and my 2p's, and I'll have one electron here, and then my 3 electrons here with the same state. Okay? Because they would obey the Hund's rule. So that's my excited state. Okay, good. What does this excited state help me do in terms of explaining how carbon does methane? Well, now I have 4 unpaired electrons, which means I can form 4 bonds. And all of a sudden, we can account for tetravalence. So the tetravalence of carbon can be accounted for by the 2s electron, one of the 2s electrons being promoted into the 2pz orbital. Okay, good. That's a good start. Does that model explain why all the CH bonds are identical? Well, let's see. You remember from your Gen Chem that there are fundamental differences between the s and the p orbitals. So if I look at the carbon, and I'm going to draw the carbon's s orbital like this, and here's the s orbital of carbon. And let's make this the H orbital, the S orbital of a hydrogen. So this should be spherical. So if I draw that for CH, this is the 2s of carbon and the 1s of hydrogen. I should end up getting a bond that is, so here's where the nucleus is. Right? So here are the nuclei. I will get a bond that has that length. So my bond length R would be that number. Okay, that's my R, that's my bond length. So this is the 2s of a carbon, the 2s of carbon bonding with the 1s of a hydrogen. 2s, 1s, short bond. What does a 2p orbital look like? Well, the 2p orbital looks like this. So if the 2p orbital of the carbon bonds with the 1s of a hydrogen, what I would get is a bond that is significantly longer. So here's my nucleus, that's my bond length. So if carbon bonds from its excited state, and again, we're ignoring the 1s because they're core electrons, we're never going to bother with those. If carbon bonds from its excited state, I should form one bond that is short and strong from 2s, 1s overlap. Well, then I should form 3 bonds that are identical to each other, that are longer and therefore weaker. So I should get 2 types of bonds, a short, strong one, and then 3 long, weak ones. But that's not what I observe. I observe in methane that all the CH bonds are identical. So carbon cannot be using the excited state to bond. The excited state accounts for the tetravalence, but it doesn't account for the fact that all the bonds are identical. In fact, if you go one step further, and by the way, that's enough to discount that model. If you don't account for everything, right? If there's one thing you don't account for, then you're out. So I can dismiss it based upon the fact that it doesn't account for number 2. But I'm just going to be even nastier. It turns out it doesn't account for 3 either. Because the p orbitals are mutually perpendicular to each other. They're orthogonal. So the p orbitals are orthogonal, which means that they're mutually perpendicular. Right? So they are mutually perpendicular. So you know that, for example, if I call these my x, y, and z axes, so I call this my y, let's call this my x, let's call this my z, the p orbitals are aligned along those axes. So my 2py looks like that, my 2px looks like that, and my 2pz is coming out of the board and going back. So when they overlap with a hydrogen, let's say a 1s comes along here, and a 1s comes along here, and a 1s comes along here, what I would have gotten would have been CH bonds that were perpendicular to each other. In other words, a bond angle now of 90 degrees. And that's not what I observed. The bond angle I observed is 109.5. It's a classic tetrahedron. So there's clearly something wrong with the model. The excited state cannot be the state from which carbon bonds. Okay. So how does it bond? Remember we mentioned hybridization? When an atom is bonding in an anomalous fashion, we invoke hybridization. So what are we going to do? We're going to say that the 2s atomic orbital will mix or hybridize with the 2p orbitals. Now this is important. I have 1s that I'm going to mix with 3 p's. If I put in 4 orbitals, an s and 3 p's, I must get 4 orbitals out. Right? Orbital conservation. I mix the 1s to the 1s, I got the sigma 1s and the sigma star 1s. 2 for 2. If I am mixing 4, I must get 4. So let's look at a hybridized state. 1s2, untouched. And I'm going to mix the s with 3 p's. And I'm going to get 2sp3, 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 2sp3. So let's talk about the numbers first, what the designations mean. The 2 indicates the principal quantum number at the energy level, right? This is the second energy level, right? And 1, 2. This tells me which energy level the interacting orbitals are from. They're all level 2. A 2s and a 2p will give the orbitals, the hybrids that are 2. There is a 1 understood by the s, but we don't write the 1. In the same way, if I write HCl, I don't write H1Cl1, the 1 is understood. So I will ignore this 1, and what this tells me is that I have orbitals that have 1 part s and 3 parts p. Of course they do. I mixed 1 part s and 3 parts p. Okay? Now, where are my electrons? So when I had a pure s atomic orbital and 3 pure p atomic orbitals, they were the houses that held the electrons. The orbitals come together and merge. Those atomic orbitals blink out of existence to be immediately replaced by the hybrid orbitals, the sp3s. The electrons that were in the s and the 3p's must now occupy the sp3s, because that's the new hole. Well, how will they occupy them? Well, the sp3s are degenerate. They're equi-energetic, right? They are degenerate, which in science means they are equi-energetic. In other words, they have the same energy. So according to Hund's rule, they will occupy those orbitals singly before they spin pair. So those 4 electrons, 1, 2, 3, 4, will go into the sp3s 1, 2, 3, 4. So the configuration for the hybridization state is 2 sp3 2 sp3 and so on. The 2 refers to the principal quantum number, the major energy level. I have a single part s and 3 parts p with 1 electron in the orbital. So the superscript refers to the occupation of the orbital. It might be interesting to look at these in terms of energy levels. So for example, where do the energy levels lie? So let's say I had a 2s, and this, I'm going to magnify this here. So here's my 2s, and here are my 2p's. Okay? Where is the energy of my sp3 hybrid? A hybrid is a mixture, right? Where is the energy of my sp3 hybrid? Well, let's see. The hybrids have 1 part s and 3 parts p. So really, they are 25% s and 75% p. So they are more p-like than they are s-like. 3 to 1, in fact. So if I were to break up this distance between the s and the p in quarters, right, these are the 2p's, my sp3 hybrids would be at that level, right? 1 part, 2 parts, 3 parts, 4 parts. The energy levels of my sp3 hybrids would be here. And while I originally had 1s and 3p's, my sp3 hybrids will be here. 1, 2, 3, 4. These are the 2 sp3 hybrids. They are more stable than the p, but they're not as stable as the s. Right? And instead of having this configuration, the configuration I now have is this. Right? So this represents that. Okay. How does hybridizing explain the properties of carbon and methane? Well, for one thing, I've got 4 unpaired electrons. That leads to tetravalence, right? Right? I have 1 unpaired electron, 1 single bond. 2 unpaired electrons, 2 bonds, and so on. So I can explain tetravalence. Well, that's good, but the excited state could also do that. What else does the hybridization state explain? Well, all of the carbon-based orbitals that go into bonding are exactly alike. They're all 2 sp3. And if you remember, the reason that we got different types of orbitals, different types of bonds, when carbon was just in the excited state, was that I had a 2s, one type, and 3 2p's, a second type. So they gave rise to 2s, 1s overlap, short strong bond, and 2p, 1s overlap, long weak bonds. That's not happening here. All of these bonds are sp3. So they're all of identical type. So when the sp3 of a carbon overlaps with the s of a hydrogen, all the bonds are identical. So I can explain both the tetravalence of carbon and the fact that all of the bonds, the CH bonds, are identical. Well, that's an improvement. Litmus test. Does it explain the tetrahedral nature of the bond? Well, let's see. We no longer have 3 orthogonal p orbitals. We now have 4 sp3 hybrids. And those 4 sp3 hybrids each have 1 electron. So there's going to be repulsion of those 4 sites of electron density around the central carbon. You remember from your VSEPR theory, your valence shell electron pair repulsion theory, that if I have 4 sites of electron density, 4 domains around an atom, they repel each other into a tetrahedron. So once I make this system, those 4 hybrids repel each other into a tetrahedron that looks like, now, I won't be able to draw all of it because the sp3 hybrid, I'm going to draw it looking like this, but there'll be a piece of it that hangs down like this. I'm going to ignore that piece because it's not really involved in bonding, right? You want a bond where there's the most electron density. So I'm going to ignore the little vestigial piece at the bottom, and I'm just going to draw the carbon, right? So here is the bonding lobe, and then I've got another one here, and another one here, and another one coming out the board. And now what happens is that the 1s of a hydrogen with its 1 electron, right, comes and bonds, let's put it here. The 1s electron comes and bonds with the sp3 of the carbons, right, and they approach each other in an end-on fashion, right? So they approach along the same line, right? This way, that way, this way, that way, right? And what we end up getting then, this is H, and again this is carbon. So what you get is this thing. Now the bonds are all formed by end-on or collinear overlap. Remember, we call those sigma bonds. So I end up with a tetrahedral structure because once I have single electrons in the sp3 hybrids, they determine the shape of the molecule. So those single electrons repel each other into a tetrahedron because you don't have to be pairs of electrons. Heck, you don't even have to be electrons. It could be 4, if you could, have 4 north poles or 4 south poles or 4 positive charges, they repel into a tetrahedron. So 4 single electrons will do exactly the same thing. So the tetrahedral shape was determined at the hybridization point. And all the H does is simply inherits the shape. Okay, so my sp3 hybridization accounts for the tetravalence of carbon, the identical nature of all the CH bonds, and the tetrahedral structure of methane. One other point. What does the sp3 hybrid look like? Well, we said that, you know, if you draw a 2s would probably look a 2s would probably look like this. Right? It's spherical and relatively small and relatively low energy. A 2p, okay, I'll come back to that. So a 2p would be larger. In fact, so I'll do it here. So that's my 2s. So they're the same energy level, same energy axis. Right? So that's my 2s. A 2p would look like this. So it's higher in energy, and it looks something like that. Right? That's my 2p. The sp3, which is lower in energy, is going to have more p character than it has s character. So it look more p-like than s-like. So what will it be? First of all, in terms of energy, it'll be at this energy level. And just to make room, I'm going to go over here. And it will look something like this. It's going to be rounder and it'll have less of the p tail than this one does. Right? So it will be smaller, rounder, right? It's morphing into S, so you won't have two equal lobes anymore. Right? So this is what the sp3 hybrid looks like. Okay? More P-like than S-like. But it certainly has S character. Okay, good. Let's look at a different hydrocarbon. And we've talked about alkenes, carbon-carbon double bonds. Let's look at the simplest alkene. And that compound is called ethene. And it has the formula, well, it's C2H4. And it has this structure. What are the features? Well, the carbon is tetravalent, 1, 2, 3, 4. That's good. Turns out all the CH bonds are also identical. Okay, that's good. The molecule is no longer tetrahedral. The molecule is planar, meaning it's flat. It's in a plane, in this case the plane of the board. The molecule is planar, but the carbon, each carbon is trigonal planar. In other words, each carbon sits at the center of a flat triangle. And you can see that here, right? You can imagine this as being a triangle. So each carbon sits at a triangle. So that the two flat triangles merge, if you will, and you make a planar structure. But there's a fourth feature, which is there are two types of carbon-carbon bonds. Okay. Those are my observations of the carbon and ethene, the bonding in ethene. And I want to account for them based upon carbon's electron configuration. Now I have a heads up. If we're saying tetravalence, it means we are long past the notion that carbon is bonding via the 1s2, 2s2, 2px1, 2py1, 2pz1, 2pz0. We know that accounts for nothing. That's the ground state. If we go to the excited state, we have 1s2, 2s1, 2px1, 2py1, 2pz1. And we know that accounts for tetravalence, doesn't account for anything else. So I can clearly tell immediately, I'm not going to get identical CH bonds if I'm using different types of orbitals. So I'm going to hybridize again. That's how I account for atoms behaving oddly. The problem is, if I try to do sp3 hybridization, well, I'm going to end up with tetrahedral structures. There's no way to get a planar system with sp3 hybridization. So instead, we're going to hybridize the lone S, and again we're going to ignore these. We're going to hybridize the S with 2 of the P's. I'm going to hybridize the S with 2 P's. So what do I get? I'm going to get, in my hybridized state, 1s2 untouched, 2sp2, 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 and then my unhybridized 2pz1. So just be clear, we didn't touch this one, so it remains unhybridized. Okay, let's detail how we get these. First of all, how many orbitals am I interacting? The answer is 3. An S and 2 P's. So I put in 3, I must get 3 out. 1, 2, 3, 1, 2, 3. Okay, great. What's the composition? 1 part S, 2 parts P. So the orbitals will have 1 part S, there's a 1 understood here. 1 part S, 2 parts P. What are the energy levels of the component orbitals? Well, in the second energy level. So it's 2sp2. And there are 3 of them. Okay. Where are the electrons? Well, there were 3 of them to begin with. They merged, the orbitals merged, poofed out of existence, replaced by these, and the electrons now occupy them. These are degenerate. So according to all 4 principles, according to the Hund's rule, they'll go 1, 1, 1 with the same spin. 4 unpaired electrons. Tetravalents. Okay. How does that account for the rest of it? Well, I'm going to erase this and come back to it later. How does it account for the rest of it? So let's diagram what a carbon in this predicament looks like. It's got 3 sp2 hybrids, each with 1 electron. And it's got a 2pz orbital with 1 electron. So I could ask, well, geez, if there are 4 unpaired electrons, why don't they repel each other into a tetrahedron? 4 electrons are 4 electrons, and that's true. But the orbitals are different. Remember, and I just erased it, remember, as you get S character, 3 things happen to you. Well, 2 things happen to you. 3 things happen to you. 1 is you get rounder, which is neither here nor there. 2, you get smaller, which is very important. And 3, your energy content goes down. If you get smaller, it means that your electron cloud literally is closer to the nucleus. So I, in essence, have an electron in a p orbital, okay? And then I have electrons in sp2 hybrids. Well, clearly, if I have 3 electrons in the sp2 hybrids, I can tell that that electron is closer to the nucleus than that electron. And I'm picking the swell as the region where the electron is most likely to be, right? So, although I have 4 sites of electron density, electrons in p orbitals are so far from the nucleus, they don't exert repulsion. Because what does repulsion depend upon? It depends on the distance between the interacting particles. If I have my carbon nucleus here, and my p electron is here, because it's in a p orbital, but my sp2 electrons, which have a lot of s character, a third s character, are close to the nucleus, well, these electrons feel each other more than they feel this one. So these are too far from the action to exert any repulsion or to have any shape-determining effect. So I'm going to ignore this electron. It's too far from the nucleus, too far from the other electrons, other orbitals, to exert any repulsion. So I have 3 sites of shape-determining electron density. So they repel into a flat triangle, VSTPR theory. So what I get is my sp2s aligned along a flat triangle, trigonal planar arrangement. And it looked like this. That's fine, that's one, that's another one. So dot, dot, dot. So these are sp2s with 1 electron, and this is my pz, 1 electron. Let's imagine another carbon comes along in the same scenario. So there are 2 carbons. This is going to have its p orbital, it'll have an sp2 hybrid, and it'll have the other 2 sp2 hybrids. And that's my pz. And again, it's a very bad thing really to put a dot for an electron, but it makes the cartoon makes it a little bit easier. What we're going to do is to have the 2 sp2s move towards each other and overlap, make a bond. I'm going to have the 1s of hydrogen with its lone electron come along and make a bond, and they will overlap this way. And I'm going to do that here as well, right? 1 electron, and then 1 electron. And they're going to overlap end on. So what we're going to get is this scenario. I'll have my carbon. I'm going to draw my bond as a line. An H, an H, and an H. Right? So these are behind the board. 1 here, 1 here. These are in front of the board. This is in the plane of the board, and then I have my p orbitals like this, each with 1 electron. Well, that's not good because my carbon does not have an octet. It's got 2, 4, 6, and 1 is 7. Close. So this carbon, 2, 4, 6, and 1 is 7. So what I want to do is to get these electrons paired. So everybody has an octet. So the carbons have an octet. The problem is, I've made the sigma bond, right? So these bonds, because they're formed by end-on overlap, are all sigma. I've made my sigma bond. So you can imagine my elbows are the carbon nuclei. So I've got a bond between them here. So they're bonded. These are the p orbitals. And I can only draw 1 lobe up. It is physically impossible to get these 2 to overlap end-on. See what happens? If I try to make them overlap end-on, the sigma bond between the carbon, that I give that up. So I can't make that, it's a geometric impossibility for them to overlap end-on. So what they're going to do is overlap side-on. Right? These are going to lean into each other and overlap, top lobe and bottom lobe. So what I'll get is what's often referred to as the banana-shaped bond. So here are the H's, and I'll make a bond that looks like this, and that's called the pi bond. So when I look at ethene, and it can simply be drawn then as this. Right? And that is drawn, it's drawn flat like this, where the H's are coming out, and then these are going back. So these H's are coming back into the board, I'm moving back into the board. These H's are coming in front. If I take that molecule and I turn it this way, everybody's going to plane the page, and that's this one. Okay? Is that consistent with my observations? Well, let's see. 1, 2, 3, 4 bonds, tetravalence. All of the CH bonds are identical, and of course they are. They're formed from the same basis set of orbitals. sp2 on the carbon and s on the hydrogen. If I use the same types of orbitals across the different atoms, the bonds are going to be the same. So I make 4 identical bonds. The molecule is planar, with each carbon being trigonal planar. Well, of course. The carbons are trigonal planar because the sp2 hybridization creates 3 sites of electron density that have S character, so they're very close to the nucleus and by extension close to each other. So repulsion is massive. There's 1 electron in a p orbital that is miles away from the action, so it doesn't interact. Not in any sort of meaningful way, because again, the force repulsion depends on how far apart you are. You're miles away, your force repulsion is minimal. So these 3 are where the action are. They repel into a trigonal planar arrangement. And then the 2 trig planar structures, atoms, then simply come and overlap, so the entire structure now is flat. That's what we observe. There are 2 types of bonds. One type is formed by end-on overlap, in this case of the sp2 hybrids. The other one is formed by side-on overlap of the p orbitals. So there are 2 completely different types of bonds. One bond is sigma, the other is pi. Now I'll make a point here. You notice that we have looked already at 3 different types of sigma bonds. When we did methane, right? In methane we had a bond that was between the sp3 of carbon and the s of hydrogen. And that bond was sigma. So there's a sigma bond between the sp3 of carbon and the s of hydrogen. We have a sigma bond between the sp2 of carbon and the sp2 of carbon. We have sigma bonds between the sp2 of carbon and the s of hydrogen. So what this is telling me is, sigma doesn't really care who the participants are. sp3, sp2, s, doesn't matter. What sigma cares about is how they interact. Sigma orbitals are formed by end-on or collinear overlap, regardless of the type of orbital. It could be pure, like an S. It could be hybrid, like an sp2 or an sp3, or they can both be hybrid, sp2, sp2. In fact, for that matter, we saw the sigma bond in hydrogen, in H2, and that was SS. So sigma doesn't care who interacts. It cares how they interact. End-on, sigma. Pi is different. Pi is formed by side-on overlap, but specifically of p orbitals. So pi cares about who and how. They must be p, and they must overlap sideways, side-on. Right? So side-on overlap is also called collateral overlap. It's called collateral. Same as side-on. Right? Because they're in the same plane. Right? So I've got 2 in the same plane and they overlap this way. Let's do the last type, and then I'll come back and show you relative energies. I will point out that if I were asked about the contribution or the character of these orbitals